Mr. Hayes, we're here for lesson 6.3, which focuses on binomial and geometric random variables. Now, this video is going to focus just on the two highlighted learning targets there off to the side. We're going to look at how to determine whether the conditions for a binomial setting are met. So we need to first define what is a binomial random variable and what are the conditions that tell us it's a binomial random variable. Then we're going to use those and say, okay, now that's binomial, let's compute the probability, let's interpret the probability of that binomial setting. So that's where this video is going to focus. The other videos will go through the other two remaining learning targets. So before we begin, and I said I know this video is going to focus on just binomial, but I want you to understand what's the difference between binomial and geometric when it comes to random variables. And so here's a blue screen. Now this blue screen does a very brief outline of what's a binomial versus what's a geometric setting. Binomial looks at the number of successes in a fixed number of trials. So you count the number of successes. So in a binomial setting, it's how many successes were there. So if you want to know the probability of making exactly 6 out of 8 free throws, when you know your probability of success of making a free throw is 0.62, well, that's a binomial setting because you're counting the number of successes, 6 free throws. Even in the other setting, if a couple wants to have at least 3 boys, what's the probability of having at least 3 boys when a couple decides to have 5 children? That itself is a binomial setting too, because there is a count for the number of successes. You could either have 3, 4, or 5 boys. And so therefore that is a binomial. Now, what a geometric is it counts the number of trials until you reach success. And that's something a little bit different. So this scenario says if you think about the probability of the first defective battery being the 4th one tested. Well, the first one worked, the second one worked, the third one worked, but then the 4th one didn't work. That is now saying, okay, I want to have a certain number of trials until a success occurs. So that's briefly what a geometric is. Again, covered in a future video. So let's just go into binomial. And so a binomial setting, what we're used to when it comes to probability is we are used to that first sentence where we're often interested in whether a particular outcome occurs. Flipping a coin, do I get heads or tails? After many repetitions on it. And, okay, if I keep going, okay, do I get another heads? Do I get another tails? I'm looking at, chapter 5 probability. But then you could also think of it as, well, what happens if I have, I'm gonna flip that coin 10 times. And how many times am I going to get 6 heads? What's the probability of getting 6 heads when I flip the coin 10 times? Now I'm changing it because right here I have a fixed number of trials. I'm saying that I want to flip the coin 10 times. And I have a number of successes I'm looking for. I'm interested in a particular event 6 times. How many times do I get heads? 6, I want to look at 6 times. So this is a binomial setting. And so in a binomial setting, it's when we perform several independent, I want you as the student, you circle, you highlight, you underline that word independent. That's a crucial word. Trials of the same chance process, and you record the number of times a particular outcome occurs. That's just saying, okay, again, think about flipping a coin. Flip a coin 10 times. How many times do I get 6 heads? What's the probability of getting 6 heads? That is a binomial setting. So when you're checking a binomial setting, you need to check the bins. And so we see right here, we call them bins. Those are your conditions. So here's what bins stands for. Bins you have, is it binary? Which means, can you define? And so right here, when you're checking the bins, you need to define. If you don't define it, you don't get to use it. I think I've said that all last chapter. So define binary. What's a success? What's a failure in the setting? Flipping a coin 10 times, I said heads. So success is me getting heads and failure is getting a tails. So I can define that setting as a binary. Independent, I told you to circle or highlight that one, is independent says trials must be independent of each other. Knowing the result of one trial must not have any effect on the result of any other trial. Checking the bins, I'm now on N. So N is number. Is there a fixed number of trials? Is there a set number of trials that are defined in advance? So it's not just, it has to be defined before you start the probability, before you start the event. So is there a fixed number of trials? And then S is the probability for success consistent? Flipping a coin, no matter what, you have a 50-50 shot of getting ahead. So is the probability of success the exact same in all the trials? So the probability of success cannot change over each trial. It has to be constant on it. So that's bins. Whenever you want to know a binomial setting, the conditions are check the bins. Is it binary? Is it independent? Is there a fixed number of trials? And what is the probability of success? And is that probability constant? So there we go when it comes to our binomial setting. Before we move on, let's go, whoa, wait a minute. Blue screen. Let's read this because this has AP Common Exam error. Now here's what happens. In Chapter 6, binomial settings and geometric settings, they're going to make sense because all you're learning is Chapter 6. But when you start to do a comprehensive or a cumulative test, which is the AP exam itself, you are going to look at all the content at one time. And so a lot of questions that involve binomial settings, students don't recognize because there's other settings we're going to look at in the future as well. So one thing to be aware of is that a lot of the free response questions on the AP exam, the ones that deal with binomial, are some of the lowest ones. So make sure when you're reading a prompt, again, it's Chapter 6, you know you're dealing with binomial and geometric in the settings, I get it. But something to practice is when you read a prompt is make sure to check the conditions. Identify what you're being asked. And one way to do it is when you read a prompt and you're not sure how to compute the probability, check the bins. Is it binary on it? And if it is, great, do a binary setting. If it's not, then we'll go learn what the other possibilities are for it. So let's move on now. When you go through this, we're used to normal distributions. We had our own notation for it. N parentheses, our mean, comma, our standard deviation, parentheses. We're used to that. We're now going to use this same idea for binomial settings. We're going to use not the same notation, but we're going to use a notation for it to help us state we have a binomial setting, just like we're expected to state that we have a normal distribution setting. So here we go. If you're considering tossing a coin n times, each toss gives either heads or tails. When knowing the outcome of one toss does not change the probability of an outcome of another toss. That makes sense. That's independence. If we define the probability of success to be heads, then we say P, the probability of success, would be 0.5. In this case, the number of heads, n tosses, so I flip the coin n times, in a binomial random setting is the variable x. We call this a binomial distribution for the variable x. And so here we are. We have a count. We count x of successes in a binomial setting random variable. So we're going to count how many successes of x we're going to have. And we have a fixed number of trials we're looking at. We're looking at n trials. And we have a fixed success probability. P is the probability of success. So in that case, think about some of the things I've said. It's either heads or tails. There's binary because success is heads, failure is tails. Is it independent? Well, that was addressed at the beginning of the prompt. One toss does not influence the next toss. It does not change the probability of the next toss to come in line. And then I have n. Is there a fixed number of trials? And so right here, n is the number of trials. And S for success, the probability, P, is success. So we have a binomial setting. When you're dealing with a binomial setting, your notation is right here. Your random variable x, right there, your random variable x, is going to be defined as b for binary, parentheses, n, the number of trials, comma, p, the probability of success. That's how you're going to define a binomial distribution. Is you're going to use b parentheses n comma p. It's binary. I'm going to have n trials. The probability of success is p for each trial. When you're checking the conditions, be sure to check the bins. Make sure you're being asked to count the number of successes in a fixed number of trials. That's a binomial random variable. And this is the important notation that we're going to use for it. So let's give it a shot. All right, so what is the probability that exactly 2 of 4 consumers will have some frustration with the setup of their new electronic device if the probability of frustration is 0.2 for any given customer? So in this case, if I'm checking the bins, each observation falls into one of, well, 2 categories. And here's the interesting part, is success is being frustrated. Failure is not being frustrated. At least defined in this prompt you see here is, hey, the probability of frustration, we're defining success as being frustrated. And we're defining failure as not being frustrated in this situation. So there are 2 outcomes, frustration, not frustration. So therefore it's binary. And we have here that the observations are independent of each other. You know, one call is not going to be affected by another call with the consumer. One consumer's frustration is not going to be affected by another consumer's frustration. And we have a fixed or a set number of trials. We have 2 out of 4 customers. So 4 is our fixed number of trials. And I have, S, checking the bins, the probability of success is the probability of being frustrated, which is 0.2. And it's the same in every observation. So this is checking your binomial setting, checking your bins. And so we have 2 categories, binary. They're independent of each other. Calling one person checking the frustration level is not going to be the same as calling another consumer. There's a fixed number of trials, n equals 4, and there is a fixed success probability, p equals 0.2. There we are checking our bins. So now we have blue screen. So let's pay attention. If you shuffle a deck of cards, we're going to check the bins here, and we turn over the top card. We put the card back in the deck and shuffle again, and we repeat this process 10 times. X equals the number of aces you observe. So is this a binomial setting? If I were to check my bins, is this a binomial setting? Well, is it binary? Well, X is the number of aces you observe, so I want to draw an ace or not an ace. That is binary. Is it independent? Well, if you read this prompt carefully, you would see I replace the card each time and I shuffle again. So therefore it is independent. Now, I should be writing these down, but they're on the next slide. Spoiler alert. But we will go through that. You should be writing these down as you're doing them. Is there a fixed number of trials? Well, it says you're repeating this process 10 times. Is there a fixed probability of success? Is that a constant probability? Well, drawing an ace is going to be 4 out of 52. And since I'm putting the cards back in the deck and shuffling again, it's going to be 4 out of 52 every time I draw. So I think there is a fixed probability of success. So let's see. Number 1, is it binary? I'm saying yes. Success is an ace, failure is not an ace. Perfect. Is it independent? Well, we're replacing the cards, so yes it is. 10 trials, there's the N for bins, and checking the success, I was right, 4 out of 52. Since all the conditions are met, I can say it is a binomial setting. I'm good at this. Choose 3 students at random from your class, and let Y equal the number who are over 6 feet tall. So is this binary? Well, if I'm looking at students, they're either going to be over 6 feet tall or they're going to be under 6 feet tall. So I think I can define this as two categories. Success being over 6 feet and failure being under 6 feet. And then I have what? Independent. Well, if I'm picking 3 students, and just think about it, visualize having 3 students. So I go, okay, 1, 2, 3. I didn't replace the students after I chose them. I just chose 3 at one time. So after I picked that first student out, I now have a fewer number of students to choose from. I'm thinking that's going to change. I don't think there's independence there. Now, if I have n, I would imagine my class size is going to be constant. And then success, I'm assuming there might be a probability of success that would be constant in the class as well, over 6 feet versus under 6 feet. But I don't think independence works here. So let's see. If I'm looking at this one, success, good. It is 2 categories. We're selecting without replacement. That's what I described. So therefore, independence doesn't work. So right here, it's not a binomial setting. As soon as I see that this one did not meet, I can say right away it is not a binomial setting because independence did not get met. The third one, flip a coin. If it's heads, roll a 6-sided die. If it's tails, roll an 8-sided die. Repeat this process 5 times and let W be the number of 5s you roll. So I'm just going to go right here. Is it binary? Well, you're either going to roll a 5 or you're not going to roll a 5. So yes. Is it independent? Because you're rolling a die, the outcome of any one trial does not affect the outcome of another trial. So if I roll the die, it's not going to matter if I roll it again or roll it again. It's going to have a set independent probability. It's not going to be affected by the previous ones. Is there a fixed number of trials? Yes. However, is the probability of success the same? No. Because in this setting, based off of what happens with that coin, I'm either going to roll a 6-sided die or I'm going to roll an 8-sided die. Those have different probabilities. The probability of success is not the same. So therefore, success is not met. So this is not a binomial setting. So this is how you check your bins. Is you need to go through and read it and think, okay, is it binary? Are outcomes independent of each other? Is there a fixed number of trials? And is the probability of success constant for each trial? Moving on. Here we go. In a binomial setting, we define a random variable x as the number of successes in n independent trials. I mean, look at how that is set. Successes in n independent trials. I mean, doesn't that kind of look like we're setting up bins there? Even this prompt right here, I can see bins, a binomial, binary setting. X is the number of successes, n is in the number of trials, and they're independent. Beautiful. It's like it's speaking to you in bins. So here you go. Here's an example. Each child of a particular pair of parents has a probability of 0.25 of having type O blood. Genetics say that children receive genes from each of the parents independently. So look at this prompt. If you're checking bins here, I can see it's defining independence for me. So that's great. If these parents have 5 children, and we're going to define X as the number of children with type O blood, well, look at this. We have a fixed number of trials. So if I'm thinking my bins, right now I'm told they're independent. I know there's a fixed number of trials, and I'm told the probability of success is 0.25. Is it binary? Well, if we keep reading, it is. Because a child's either going to have type O blood, success, or they're not going to have type O blood, failure. And so notice they're defining S as success and P as failure. Now, if I want to know what's the probability of having X equals 2 successes. Well, you can see I have this listed out for you. You could have 2 children with type O blood, success, success, and then 3 children with failure, not type O blood. However, if you think about birth order, it's not like the first 2 are guaranteed to have O blood and the last 3 are not. I mean, the type O blood could come from the 3rd child or the 5th child. It could be the 4th child, 5th child. It could be the 2nd and the 4th or the 2nd and the 5th. There's so many combinations on it. In fact, there's really 10 different arrangements. So that one probability that we see highlighted in that blue there, that one probability is just for one arrangement. But there's really 10 different arrangements of these. And there they are. All the different successes and failure arrangements that you could have in this case. Now, what does this mean? This means that we can have a probability of x equals 2. We are going to use that probability that we did before, that 0.025 squared times 0.75 to the third. Now, I didn't really talk about this part right here. I apologize. This is the probability of success, and if 25% is the probability for success, then 75% is the probability for failure. So that's where we get the 0.75. If success is 0.25, failure is 1 minus that, so it's 0.75. And so I have 2 successes, so 0.25 squared. I have 3 failures, 0.75 cubed. But I have 10 arrangements of those. We see it off to the side, so really I have 10 times that, which will give me 0.2637. That's the answer in this case. Is it binary? Yes, I checked the bins while I was reading it. And the issue, though, is when we do it and we think about, okay, well, I have 2 successes, 0.25 squared. I have 3 failures, 0.75 cubed. That's right. But that's only for one arrangement. You have 10 different arrangements. So I have to multiply that by 10. So we can see the formula for our binomial setting is broken into a couple parts. And here are those parts. We see right here is your probability, and I'll just use S as success, so I'm going to use P. We can see we define P as a probability of success, and that's going to occur a defined number of times, a set number of times based off our prompt. I'm going to call that K. And we're going to have failure. Well, failure, we did 1 minus P. 1 minus 0.25 gave me the 0.75. Now, how many failures did I have? Well, if I had, 5 children and I had 2 successes, well, I did 5 minus 2 to get 3 failures. So I did my N minus my K. It's really success raised to the power of how many successes are you looking for, and then failure raised to the power of how many failures are left. But you have this part right there. You have that coefficient in front which looks at the different number of arrangements. And I wish there was a way for us to calculate that so we didn't have to draw it out every single time. Oh wait, there is. And so here we are is how do we calculate that coefficient? You like how I used the word coefficient on the previous slide? It linked it together, didn't it? And so in this case, we had 10 different arrangements. Those number of arrangements are used as the coefficient in your formula. So you can see right here is kind of what I wrote down on the previous slide. So the binomial coefficient, the number of arrangements in a binomial setting, is found by using your combinations formula, NCK. Another notation is you could use C parentheses N comma K. Another notation, and this is kind of one you probably would see on more multiple choice questions, is right here. So I know you're only writing down the highlighted portion, but if I were a student right now, I would also make sure I combine this one in there. That's another way. All 3 of those are fair game for you. They mean the same exact thing. N is the number of trials. K is looking at the number of successes. So what we have on top is we have N factorial. That's not N yelled really loud. It's N factorial. Remember, factorial, the exclamation point, means you multiply by every integer less than that. So if I have 5 factorial, it's going to be 5 times 4 times 3 times 2 times 1. Boom. And then I'm going to do, 7 factorial. 7 times 6 times 5 times 4 times 3 times 2 times 1. That's factorial. You do need to remember, though, that 0 factorial is 1 in this case. So here is the formula for it. You have n factorial over k factorial times n minus k factorial. You have your total number of trials over how many successes factorial, and then how many failures factorial for it. All right, so let's give it a shot. And when you think about it, here's what we're looking at in this case. We can look at our entire formula in a different way, but here's the stuff that we went through before. We're going to kind of talk about the binomial coefficient. I already talked about what factorial means. So this means 4 times 3 times 2 times 1. This means 3 times 2 times 1. This means 2 times 1. This just means 1. This 0 factorial is 1. So this number would be 24, this number would be 6, and this number would be 2. That's factorial. Let's give it a shot with this problem right here. If I have 12C5, I have 12 objects, I'm looking at how many combinations of 5 groupings can I have. I'm going to write this out in my formula. Now this is my n and this is my k. So I'm going to have 12 factorial over k, which is 5 factorial. And then I'm going to do n minus k. So 12 minus 5 is 7 factorial. Now I know right above me is the calculator, but where's the fun in that? And now if I look at this, I want to show you, if I do this, 10 times 9, I work my way down. Notice once I get, and I'm not going to bother, once I get to 7 factorial, look at what happens in the bottom. I have 5 factorial times 7 factorial. And what happens is that 7 factorial cancels out with the 7 all the way down in the top. And so really I'm going to have that left. And let me see, 12, 11, 10, in this case, 792. That's what that multiplies into. So we're good. Now, yeah, it's 792, I know, fast. But let's see why I have this next one here. If I have this same setup, which remember means the same idea, it looks at 12C7 rather than 12C5. And I set this up. I'm going to have 12 factorial over 7 factorial, 7 successes. That means I'm going to have 5 failures. I'm not even going to bother to write it out because I can look at this and I can look at this and I can see it's the same denominator. They're just flipped on multiplication, and commutative property for multiplication says that doesn't matter. I'm going to get 792 here. So that's interesting. There's 2 different number of successes here, 5 and 7, using the same number of trials, 12. It has the same binomial coefficient. This is really interesting that it happened because maybe there's something there. Maybe there's a pattern there, and maybe a mathematician would figure out this pattern to help us out. Oh, there was one. We call him Blaise Pascal, and he had something called Pascal's Triangle. Pascal's Triangle, each of these represents the binomial coefficient in a setting. So this triangle really represents all the binomial coefficients, and you probably examined it in one of your other math classes as well for it. And so it's a really interesting triangle, but you really don't want to draw it out every single time. We're going to use a binomial coefficient. We're going to use the combination formula. So sorry, Blaise Pascal, I know you worked really hard on that triangle. We're going to use this instead rather than your magnificent triangle. Don't get me wrong, I like it, but this is much faster for us, so I apologize. And we're going to use our calculator in the long run to help us as well. So here we go. Here is the overall formula. You have the number of arrangements of k successes. That is how many combinations. That is your NCR, or in this case, your NCK. And you're going to multiply that by success. How many times are you looking for success as the exponent? P to the k. Then you're going to look at failure, multiply that by that probability, and raise to the power of how many failures. This is the binomial probability formula. So when you check your bins and you want to calculate your binomial probability afterwards, we would use this formula. It is also on your formula sheet, and you can see a picture right here to help you out. All right. Now, in this case, for this problem, I would check my bins. But this is I'm just going to go ahead and say it is binary. I would write it out for it, but I can see the clock on the screen, and it's not quite there. So I'm going to describe it, but you would write it. Seriously, don't just calculate the probability, write it. So I'm going to speak it, you write it. is it binary? So when I read this, success, we already actually know what we already dealt with this in a way. We dealt with this frustration problem. So good news is we already defined this. Success is frustration. Failure is not being frustrated. Independence, we said the consumers were not going to be affected by other consumers' responses, by other previous phone calls. Is there a fixed number of trials? Yes, there are 6 total trials, and we have a fixed number of successes of 2, and those 2 successes have a constant probability of 0.2. So I know it's a binomial setting. So here's what I'm going to do. I'm going to state it. It is a binomial setting. There are 6 trials. The probability of success is 0.2. Define the binomial setting like you would a normal distribution setting. You need to state it. So now let's do it. All right, so I have 6C2. That is my binomial coefficient. It's going to be multiplied by my probability of success, which is 0.2. How many successes am I looking for? I'm looking for exactly 2 successes, so to the second power. How many, well, what's my probability of failure? 0.8 then, 1 minus 0.2. How many failures? Well, if there's 2 successes in 6 trials, that means I have 4 failures. Or I could write it as 6 over 2, no fraction bar, people. No one likes that student that puts a fraction bar in the binomial coefficient shorthand. And then I have 0.2 squared times 0.8 to the 4th power. And I could type that in my calculator. And so I have my calculator here. And what I'm going to do is I'm going to type in 6 math, go over to probability. And if I go over to probability, you can see the third option is NCR. So I have 6 NCR 2. Now I can enter there. I could have done a parentheses around it in the first place. I forgot to. So I'm just going to do, I'll hit parentheses, second enter. Let's try that again. So I'm going to hit second enter, and this time I'm going to insert the parentheses in front. Whoa. I'm going to go ahead and copy. This is normally where if you were watching a movie, they would have a gag reel, and they would have all these things of what really happened. So there we go. I inserted the parentheses, and then I close it. And I do 0.2 squared. And then I do parentheses, 0.8, close it, and I'm going to raise it to the, looks like 4th power. So I get a probability of 0.24576. So I can use the NCR in my calculator to do the shorthand for it. There's my probability. Now, I used the long way. I could also use this in my calculator. And I want you to realize some calculators have it as option 0. Some of the newer calculators have it as option A. So that part's not in the notes. And so what happens is right here is how you're going to arrange it. So I'm going to go, it's a distribution. So I'm going to go to second distribution. Let me actually change my mode as well. So I'm going to hit mode. I want to go to math print. That'll make it a lot easier. So I have math print. And I'm going to go to second vars distribution. And if I go now towards the bottom, notice mine is a binomial PDF. Now, if you don't have this prompt, it's what's written over on the side there. You write down the number of trials, 6. We write down the comma, how many, what's probability of success, 0.2 on it. X is really your K value of it. How many successes am I looking for? In this case, we're looking for 2 successes. And so binomial PDF, 6, 0.2, 0.2, hit enter, you get the same answer. Now, calculator talk gets you no credit. That's why you can see I'm using my notation here, B parentheses 6, 0.2. I'm showing that I know how to use the formula, but then I can go right to my calculator for it. It also works in this case. What is the probability of having no more than 2 of 7 mall shoppers? I'm not going to check the bins. And I'm not going to write it down. Is it binary? They either agree or disagree. Binary. Is it independent? One person's opinion, if it's not going to affect another person's opinion, great. Is there a set number of trials? Yes, there's 7. So n is 7. Is there a set number of successes? Well, there is. No more than 2. You're either going to look for 0, 1, or 2. So I did check the bins. It is binary, so I'm going to state that it's binary. It's binary. I'm looking at 7 trials. The probability of success in each trial is 0.4. Define it. And now, well, no more than 2. That'd be 0 people agreeing, 1 people agreeing on it, and 2 people agreeing, because no more than 2. So really there's 3 settings I'm looking at here. So I could do my 7C0, and I can multiply by 0.4. I want no successes. I want all failures. I want no one to agree. I want everyone to disagree. I can also have the other situation here, 7C1. 1 person agree and 6 people not agree. I can have 7C2. 2 people agree and 4 people not agree. I would have to calculate all those, and I would have to go plus, plus. And when you do that, by the way, you're going to get 0.419904. But you would have to type each one individually in your calculator, and you'd have to go through it. Now, I'm going to expect you to write this down, because that is the situation of it. That's what you're trying to analyze. But I don't want you to calculate that all by hand. I really think you should probably learn how to use your calculator. And so when we go through this, we have binomial CDF. And so notice, be careful. One of them is binomial PDF. That's what we used before. And here's binomial CDF. It's the same idea. We are looking at here is 7 trials. Here's the probability of success, 0.4. Now be aware, and I will highlight again, some of the new ones are B instead of A. It's the number of trials and less for successful observations. So in this case, we said at most 2. So that's 2 or less. So here is binomial CDF. In that case, I was right, 0.419904. Amazing. There's binomial CDF. There's the setup for it. And for this case, it's just one of those things where you have to show a certain amount of work, but then go to the calculator, people. Go to the calculator. All right, so difference between binomial PDF and binomial CDF is binomial PDF points to a value. It points to it. Binomial CDF accumulates the values at that number and below that number. So if you're looking for an exact value, one value, binomial PDF. If you're looking for cumulative values, that number or less, then it's binomial CDF. All right, last one. Check the bins. They're done. Congratulations, it fit the bins. We're just going to go through this. Find the probability that exactly 3 of the children have type O blood, because it's the same prompt as before. Define it. Let X equal. Look at that. They defined it. We know X is a binomial distribution. Because they said that, I'm going to write it. It's a binomial distribution of 5 and 0.25. That way the grader knows I'm aware it's a binomial. So I want to find the probability P of exactly 3 children with type O blood. So X equals 3. So I'm going to have 5 children, 3 with type O blood. I have 0.25 as the probability of success, 3 kids with that, 0.75, and I have 2 kids without that. And in this case, is it PDF or is it CDF? And it is PDF. So I'm going to do binomial PDF because it's only one value. It's pointing to an exact number. There are 5 trials, 0.25 for the probability of success, and I'm looking for 3 successes here. So I'm going to hit enter, and there is my answer. This probability is 0.08789. There we go. So there's the amount of work that you need to know. Now, I already defined it here, so I'm not going to define it here. Same situation. Now, no more than 3 of their children have type O blood. Sorry, not if no more. Should the parents be surprised if more than 3 of their children have type O blood? Should the parents be surprised if more than 3 of their children have type O blood? Better. And so what that means is if I want probability of more than 3, well, I'm looking for 4, and so I'm going to add the probability of x equals 5. So I'm going to set up both formulas. I'm going to say I have 5 with 4 successes, so 0.25 to the 4th with 1 failure, and that represents this one. And then I'm going to do this one, the probability of 5. So I'm going to have 5, choose 5, 0.25 to the 5th, and then 0 successes, because they're all failures in that case. All right, so what do I have? I could find each of these and calculate them, and I'm going to get binomial PDF plus binomial PDF. So I can use this same setup, you see right there, and find each one. But I would change my number of successes. If I do that, I get 0.1465, and I'm going to add 0.0098. That's going to give me 0.01563. If you want proof, so here you go. Here's 4. And I will just copy this. And here's 5. I'm going to take this number and I'm going to add this number. I told you I was right. I rounded. And so there we are for it. Long video, I apologize for it, but it is a lot of concepts here and a lot of checking the bins for it. So go back, refresh your memory on what you need to know. But there we are with binomial settings. Check the bins, binary independent, number of successes being fixed, and a success probability that is constant. And then how do we find it? We do our binomial coefficient times successes to the power of how many times failure to the power of how many failures.